Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 16, and in this lecture we are going to talk about stress strain relation, particularly for isotropic materials. Okay. So, till now we saw that the stress sigma I j is summation over C I j k L into epsilon k L, right, where you have summation over k and L, and this C I j k L has got 21 independent constants. So, this is for general material, but isotropic materials have got extra symmetry in them, due to which the number of independent constants actually reduces. By isotropic material we mean that it has same property in every direction. So, what does that really mean? For example, suppose we have an isotropic material, and if we can somehow, let us say at this point we stretch the material in one direction. Okay. So, suppose this is 1, this is 2, and what comes out is 3. So, suppose that we are stretching the material in one direction, but not letting the material to stretch or compress in any other direction. Okay. So, we are only letting it stretch in one direction. So, basically the strain matrix that gets generated in this case has got only epsilon 1 1 and rest are all 0. Okay. Just suppose that we could impose such a strain in the body. Now, if you come to this formula with this strain matrix, then what will be sigma 1 1? So, sigma 1 1 for example would be summation over k L C 1 1 k L epsilon k L, is not it? But because epsilon 1 1 is only non-zero, rest all are 0, this simply means it is C 1 1 1 1 epsilon 1 1, right. Now, suppose that we do another experiment, we have the same body, but now instead of letting it stretch in one direction, you let it stretch in the second direction. Okay. So, I let it stretch in the second direction, but again not allowing it to stretch or compress in the other directions. Okay. So, the strain that would get induced at this point in such a case would be, the strain matrix would be 0 everywhere except for epsilon 2 2, is not it, because we are letting it stretch in two directions. So, there is some stretching in the second direction. So, stretching minus 1 is the strain epsilon 2 2. So, there will be a non-zero epsilon 2 2, but rest all will be 0, right. Now, with this strain matrix, let us say I want to get what is sigma 2 2. See, now I want to see sigma 2 2, not sigma 1 1. So, sigma 2 2, again you apply the formula and you have summation over k L C 2 2 k L epsilon k L, is not it? And since epsilon 2 2 is only non-zero, then this means it is C 2 2 2 2 epsilon 2 2. And if it were isotropic, what would mean is that sigma 1 1 in the first case would be same as sigma 2 2 in the second case. So, the response of the material, the response means when you apply strain, stress is getting developed in the material. So, that is the response of the material. So, the response in the first case sigma 1 1 and in the second case sigma 2 2 would be the same if this were isotropic. Now, compare these two formula. If you are applying the same strain epsilon 1 1 in the first case and epsilon 2 2 in the second case, if it is the same and it leads to the same stress, then that is possible only if C 1 1 1 is equal to C 2 2 2 2, is not it? So, that is an extra constraint if it were isotropic material. So, from physics we know that the response has to be the same. So, that means sigma 1 1 has to be sigma 2 2. So, this implies C 1 1 1 1 is equal to C 2 2 2 2. And likewise, you could also think of straining in the third direction and measuring sigma 3 3, which would further imply that this is equal to C 3 3 3 3, right. So, you see these are additional constraints, these are not covered by either minor symmetry or major symmetry that we did in the last class. So, you can see that number of independent constants are actually going to reduce, right. So, actually there is a rigorous mathematical derivation where we employ the property that the response is same in all the directions, where you stretch in one direction, two direction or at an angle, at any angle you stretch, you get the same response. So, when you apply that mathematically and work out a rigorous derivation, you are able to obtain a simpler stress strain relation, where we only have two independent constants. So, instead of 21 we would just have two independent constants. Okay. So, that is really beautiful, is not it? For isotropic material we only get two constants. So, basically you only have to do two experiments to get two constants, and then you get the complete stress strain relation, whereas for a general material you require 21 constants, which would mean that you would have to do 21 independent experiments somehow to get all those 21 constants, all right. So, of course, the general material they are called anisotropic material, for which the properties in different directions are different, all right. So, we call them anisotropic material, aniso, which means they are not the same. Iso means it is the same, but aniso means it is not the same. Okay. So, for isotropic material, so once you work out the mathematical derivation, the relation that comes out is the following. It tells us that sigma I j is equal to lambda times trace of the strain tensor plus 2 mu into epsilon I j, which is same as lambda times epsilon 1 1 plus epsilon 2 2 plus epsilon 3 3, that is the trace of the strain matrix, right, plus 2 mu into epsilon I j. So, this is a formula where stress is written in terms of strain. We have an opposite formula where strain is written in terms of stress. So, that formula tells us that epsilon 1 1 for example is 1 over some constant E, which we will say what it means, into sigma 1 1 minus nu times sigma 2 2 plus sigma 3 3. Okay. Likewise, epsilon 2 2 is 1 over E into sigma 2 2 minus nu times sigma 1 1 plus sigma 3 3. Epsilon 3 3 is then 1 over E into sigma 3 3 minus nu times sigma 1 1 plus sigma 2 2. Then the shear strength gamma 1 2, that is equal to 2 times epsilon 1 2, right, and that becomes sigma 1 2 divided by a constant called g, okay, and sigma 1 2 we know it is tau 1 2 divided by g. Likewise, for gamma 1 3 it is tau 1 3 divided by g, and gamma 2 3 equals tau 2 3 divided by g. Okay. So, you can see that on the right hand side we have 3 constants appearing here, Young's modulus E. So, E is called Young's modulus, then we have nu is called Poisson's ratio, and G which is called shear modulus of elasticity. So, I will write here E is the Young's modulus of elasticity, nu this is called Poisson's ratio, G this is called shear modulus of elasticity. Okay. On the left hand side we have 2 constants lambda and mu. So, they are called Lamé's constants. Okay. So, after a mechanician Lamé, it is called Lamé's constants. And if you just look at, let us say I equal to 1 and j equal to 1, then sigma 1 1 is actually lambda times epsilon 1 1 plus epsilon 2 2 plus epsilon 3 3 plus 2 mu epsilon 1 1, is not it? Can you see what is C 1 1 1 1 for example? So, C 1 1 1 1 relates sigma 1 1 and epsilon 1 1, is not it? So, that means C 1 1 1 1 you can read from here is lambda plus 2 mu, right. Likewise, what is C 1 1 2 2? So, that you can also read from here, it is lambda, which is also equal to C 1 1 3 3, is not it. If you for example, work out sigma 2 2, so that would be equal to, look at the formula, put I equal to 2, j equal to 2. So, you get lambda times epsilon 1 1 plus epsilon 2 2 plus epsilon 3 3 plus 2 mu epsilon 2 2. Now, can you see what is C 2 2 2 2? So, from here C 2 2 2 2 is again lambda plus 2 mu, and you can see that it is matching with C 1 1 1 1, because for isotropic materials they have to be the same as we discussed earlier, right. Let us see what happens when I is not equal to j. So, when I is not equal to j, we are looking at the off diagonal terms, right. So, okay, I have missed out a term here. So, this should have been lambda times trace of epsilon into delta I j. Okay, so, there is a delta I j also over there. So, when I is equal to j, delta I j becomes 1, and then we get what we worked out. But when I is not equal to j, delta I j becomes 0. So, for off diagonal terms we do not get the first term becomes 0 and we simply get sigma I j equal to 2 mu epsilon I j, is not it. So, this means sigma 1 2 for example would become 2 mu epsilon 1 2, right, which is same as mu times gamma 1 2. Now, can you see the relation here? This formula and this formula right here on the right hand side. So, this implies that mu is same as g, is not it? Look here, gamma 1 2 is equal to tau 1 2 by g, and from the left hand side sigma 1 2 which is tau 1 2 is equal to mu times gamma 1 2. So, that means mu is same as g, right. Now, let us try to see what are the meaning of E, mu and g. Young's modulus, Poisson's ratio nu and g which is a shear modulus. Okay. So, Poisson's ratio is called nu, right, all right. So, look at this first formula here. What does this tell us? That the strain in one direction not only depends on stress in the same direction which is sigma 1 1, but also on the stress components in second and third direction sigma 2 2 and sigma 3 3. So, suppose that I am doing a very simple experiment, think of a very simple experiment. So, suppose that you have got a rectangular beam okay, and its length is L, the breadth is B and the height is H. Okay. And you can also give them the direction. This is E1, what goes up is E2 and along the breadth we have E3, all right. And think of applying force on this rectangular beam in one direction from both the sides. So, we are pulling the beam from both the sides. So, you see what is the cross sectional plane here? That is the one plane, its normal is E1, is not it? We are applying force on the cross sectional plane whose normal is E1, and the force that is being applied is along the cross section normal, it is in the one direction. So, what kind of stress component this is going to generate? So, this is going to generate sigma 1 1, right. This is E1 plane, and on E1 plane we have traction 1 which has 3 components sigma 1 1, tau 2 1 and tau 3 1, right. But because the applied force is along the normal, so the shear components are all 0 and we only have sigma 1 1, is not it. And what is happening in the second and third direction? You see, we are not applying anything in second and third direction. So, there is no stress on the second plane and or on third plane. So, if you cut a section with normal along E2, then on that plane you do not see any stress. Okay, you see, because on the boundary you are not applying anything. So, even within the body, if things are done carefully, there will be no traction on second plane, likewise on the third plane also. And if somebody tells you what is the state of stress, can I write down the stress matrix? Then that is simply sigma 1 1 0 0 0 0 0 0 0 0 0. 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 all right. So, this is the state of stress and it is going to generate some strain. So, it is going to generate let us say epsilon 1 also, is not it. So, the length of the beam will change for sure when you are pulling it, there will be some change let us say delta L. So, what will be epsilon 1 that is delta L by L, is not it. You remember epsilon 1 is del u 1 by del x 1, and if the elongation is uniform along the length, then del u 1 by del x 1, which is the local strain, becomes same as the global strain, which is simply delta L by L. Recall from our strain class, this was the first example that we did, is not it. So, we are applying sigma 1 and it is generating epsilon 1. It is not only generating epsilon 1, it is also generating epsilon 2. You see, when you stretch this beam in one direction, there is some contraction in the second direction and on the third direction also. You should do this experiment and you can see it. Take a really soft beam, take a soft circular beam for example, or let us say take a rubber, you elongate the rubber a lot, you will see that the cross section will reduce. So, there is change in length in the lateral direction also. So, here for example, you will get epsilon 2 and also epsilon 3. So, if you write the state of strain, the strain matrix will have epsilon 1, it will have epsilon 2 and it will also have epsilon 3. And if you are careful, the shear strength would be 0. Okay. So, that is a state of strain. Now, for this experiment, when you draw the graph of sigma 1 versus epsilon 1, so you are applying the force and you measure epsilon 1 as delta L by L, right. So, this is delta L by L. What would be epsilon 2? Epsilon 2 that would be delta H by H, right, change in length in the second direction divided by the length in the second direction, and epsilon 3 that would be delta B divided by breadth, right. So, you can measure these things when you are doing the experiment. So, when you plot sigma 1 versus epsilon 1, you will perhaps see a graph like this. So, the initial slope of this graph, you know this initial slope of this graph, that is called the E, the Young's modulus, all right. So, E is del sigma 1 over del epsilon 1 at epsilon 1 equal to 0. So, that is Young's modulus, but you see when you compute this derivative, you should not have sigma 2 or sigma 3. So, you have to stretch the beam axially, but let it freely shrink in the lateral direction. So, when you do such an experiment and plot sigma 1 versus epsilon 1, then the slope of this curve, that is the Young's modulus. Okay. You can also come to this formula, stress strain relation. Look at this first relation, epsilon 1 is equal to 1 over E sigma 1 minus nu times sigma 2 plus sigma 3. And from our experiment, we know that sigma 2 is equal to 0 and sigma 3 is also equal to 0. You plug it here, what do you get? Epsilon 1 is equal to 1 by E into sigma 1 or sigma 1 is equal to E times epsilon 1 1. So, sigma 1 1 versus epsilon 1 1 graph, what will be its slope? That is E, is not it, and that is called Young's modulus. So, according to this formula, it tells us that the slope should be constant and equal to E, but in reality the slope is not a constant, of course, it changes. So, the formula that we had there works only for a small strain, whereas here we have applied lot of strain, that is why the slope has changed. But the slope when epsilon 1 1 is very close to 0, that is the Young's modulus. Okay. All right, and what about the Poisson's ratio? So, Poisson's ratio is defined as negative times the lateral strain, lateral normal strain over the longitudinal strain. So, again from this experiment, you are pulling it in the longitudinal direction. So, that is where you are directly applying a strain, is not it? You are applying the force directly in one direction. So, it will directly induce a strain in one direction, but the strain in second and third direction, they are indirect. Due to strain in one direction, you get strain in second and third direction. Okay. So, this formula here is then minus of epsilon 2 2 by epsilon 1 1, or you could also write it as minus of epsilon 3 3 divided by epsilon 1 1. Okay. So, remember that on the denominator we have to have the direct strain. In whatever direction you are applying the force, measure the strain in the same direction. Or you could say that suppose you are applying strain itself, you are pulling the bar. So, you are directly applying the strain and then you measure the lateral strain. Okay. So, this would be then imposed longitudinal strain. So, on the denominator we have the imposed strain and on the numerator we have induced. And Poisson's ratio is negative of the ratio between the two. And for isotropic body, epsilon 2 2 by 1 1 or epsilon 3 3 by 1 1, it will give you the same value. So, it is very interesting, although in this experiment you are only applying force in one direction, still it generates strain in second and third direction, and that is you know from physics also, when you actually see the real experiment you see that. And it is also visible here, you can find it from this formula also. So, in this formula substitute sigma 2 2 and sigma 3 3 equal to 0 and see what you get. So, let us just work it out. So, epsilon 1 1 would be 1 over E times sigma 1 1, right, and epsilon 2 2, the formula says it is 1 over E into sigma 2 2 minus nu times sigma 1 1 plus sigma 3 3, is not it. So, put in sigma 2 2 equal to 0, sigma 3 3 equal to 0, and you get minus nu times sigma 1 1 by E, and sigma 1 1 by E is actually epsilon 1 1. So, you get minus nu times epsilon 1 1, right. So, you can see that nu is equal to negative of epsilon 2 2 by epsilon 1 1. So, this is of course from formula, but if you want to measure Poisson's ratio of a body, then this is the experiment that you have to do. You take a bar, you pull it measure the direct normal strain and measure the indirect or the lateral normal strain, take the ratio, you get the Poisson's ratio. If you want to get the Young's modulus, plot sigma 11 versus epsilon 11 and measure the initial slope, that gives you the Young's modulus. How to get shear modulus? So, you see as from the formula, the shear modulus it simply says tau 12 is equal to g times gamma 12. So, if you can induce shear in the body and measure the stress, then the ratio of those two will give me shear modulus, is not it. So, to measure shear modulus G, what you can do is you again take your rectangular bar. Suppose I take a rectangular bar and you clamp on the lower side, the bottom area you completely clamp it, let us say you glue it to the surface, and let us say this is one direction, this is two direction, and that is your third direction, and you apply shear force on the top surface. So, the top surface is surface with normal 2, is not it, E2. So, it is the E2 surface and you are applying force in the one direction. So, this is tau 1 2, right, and then what do you think what is going to happen as you apply that shear force? The bar is going to shear. Is not it, the bar is simply going to shear, and then what would be the shear strain? That is this angle, the change in angle between two perpendicular line elements, remember. So, initially the red lines which are perpendicular, they get inclined, and that is the change in angle, which is also gamma 1 2, is not it. So, again you draw your slope or the curve for tau 1 2 versus gamma 1 2, and you will see something like this, and you measure the initial slope. So, when you measure the initial slope, that would be the shear modulus of elasticity. So, G equals tau 1 2 divided by gamma 1 2 when gamma 1 2 goes to 0. So, when the shear strain is very small, you measure this ratio and you get shear modulus of elasticity. Okay, so, I hope you got some idea about the three constants: Young's modulus of elasticity, Poisson's ratio, and shear modulus of elasticity. And of course, you see that there are three constants here, but isotropic materials have to have only two constants, is not it. So, there is a relationship between these three constants, which is that G should be equal to E over 2 times 1 plus nu. All right. So, we learnt about Young's modulus of elasticity, we also learnt about shear modulus of elasticity. See, in the Young's modulus of elasticity, it was relating normal strain with normal stress, epsilon 1 with sigma 1. So, it was relating normal strain with normal stress. Shear modulus of elasticity was relating shear strain with shear stress, right. There is also something called bulk modulus of elasticity, which relates volumetric strain with some kind of volumetric stress or what is pressure. So, let us see what would be the formula for bulk modulus of elasticity. So, bulk modulus of elasticity so, of course, you are all familiar with this bulk modulus from your schools. So, you do it for gases. Can you recall what was this? So, we denote this by K. So, to any gas or to liquid, when you apply pressure, then the liquid shrinks, is not it, or the gas shrinks. So, there is a change in volume. So, it induces volumetric strain when you apply pressure to it, and the bulk modulus is simply negative of delta P, the change in pressure, over delta V by V. So, that is the formula for the bulk modulus of elasticity. So, this is for liquids. Now, how can we define this for solids? What is the meaning of pressure in case of solids? See, the denominator delta V by V, we know what does it mean for solids, is not it? So, for solids, delta V by V, that is nothing but volumetric strain, is not it? And we know this is equal to trace of the strain tensor, and that is also equal to epsilon 1 plus epsilon 2 plus epsilon 3. Okay. Now, what is the meaning of pressure for solids? So, you would recall that we had decomposed the stress in solids as a sum of what is called the hydrostatic state of stress and the deviatoric stress, and it is the hydrostatic state of stress which has direct relation to stress in liquids, right, where you only have pressure acting. So, can you recall what was the formula? So, for solids, the stress sigma, we wrote it as 1/3 of I1, the trace of stress, times identity plus the remaining term, the deviatoric part, and in case of liquids, the stress for liquids which is in statics, the stress sigma is minus of P times identity, is not it? So, from here when you do the comparison, you can see that the equivalent pressure P for solids would be simply minus of I1 divided by 3, and we get a minus sign because pressure is compressive in nature, is not it? So, pressure, if you want to find out pressure for solids, you simply do minus of I1 divided by 3. Okay. So, that means the bulk modulus for solids, so K for solids would simply be minus of pressure, which is minus I1 by 3 divided by delta V by V, which is trace of epsilon. So, this becomes 1/3 times trace of stress tensor divided by trace of epsilon, is not it? So, you simply compute trace of sigma divided by trace of epsilon and you will get the bulk modulus. Can we obtain it from our relationship here? Do you see this formula here? This is also called generalized Hooke's law or 3-dimensional Hooke's law. So, I will just write here. We also call this 3D Hooke's law of elasticity. We are familiar with the one dimensional Hooke's law from school, where sigma we say is equal to Young's modulus times the strain, and there we were simply stretching the bar. So, we had only one sigma and one epsilon. So, sigma was equal to E times epsilon, that is in the school, but now we have a 3 dimensional picture, we have a 3D body and we do not have one stress, we have a stress matrix, we have a strain matrix, and to relate them we need this 3D Hooke's law. Okay. So, from this 3D Hooke's law, can we obtain a relationship between stress, the trace of stress divided by trace of strain? So, I guess yes, we can do it. Why do not we simply add the first 3 equations? So, if we add the first 3 equations, on the left hand side you will get trace of strain, and on the right hand side you will have trace of stress. So, just see here. So, add the first 3 equations of 3D Hooke's law okay. So, on the left hand side you will have epsilon 1 1 plus epsilon 2 2 plus epsilon 3 3, and on the right hand side you will have 1 over E times sigma 1 1 plus sigma 2 2 plus sigma 3 3 minus nu by E, and you have sigma 2 2 plus sigma 3 3, sigma 1 1 plus sigma 3 3, and in the last one you have sigma 1 1 plus sigma 2 2. When you add all of them, you simply get 2 times sigma 1 1 plus sigma 2 2 plus sigma 3 3, is not it? So, this means that the trace of epsilon is equal to 1 minus 2 nu over E times trace of sigma, correct. And you can now plug in this here, and what we get is the bulk modulus K is then E over 3 times 1 minus 2 nu, all right. So, this is a very important relation, of course. You see that the bulk modulus is not an independent constant. If you know Young's modulus and the Poisson's ratio, use this formula to get the bulk modulus. Similarly, to get shear modulus, G is equal to E over 2 times 1 plus nu, right. And you know this formula conveys lot of things. What happens when nu gets close to 1/2? The Poisson's ratio, which measures the negative of the ratio of lateral strain over longitudinal strain. So, it is usually positive, okay. It is usually positive. It is very hard to get material with negative Poisson's ratio, but these days people are looking for materials with negative Poisson's ratio, okay. But generally the materials that you have, the Poisson's ratio is usually positive. So, that when you stretch the bar in the lateral direction, it shrinks. It is very unusual when you stretch the bar that in the lateral direction, instead of shrinking, it elongates, and of course, they are called negative Poisson's ratio material or auxetic material, which is unusual, of course. So, usually Poisson's ratio is positive, but see here what happens when the Poisson's ratio becomes close to 1/2. So, question, what happens when nu tends to 1/2? see what happens to the denominator, it is getting close to 0, 1 minus 2 nu. So, when you put nu equal to 1 half, 1 minus 2 into 1 half, it is 0. So, when nu is 0.499, it is really close to 0, right. When nu becomes 0.4999999, it gets even close to 0, and the bulk modulus becomes very large. So, what is the meaning that the bulk modulus is very large? So, look at the formula or the definition for bulk modulus. So, bulk modulus says it is delta p over the volumetric strain. So, if the bulk modulus is very large, that means if you apply some finite amount of change in pressure, then the volumetric strain that gets induced would be very small, right. That is why the ratio would have to be very large. So, the denominator has to be very small, is not it? Then only k can be very large. So, think of what kind of material would that be. You are applying lot of pressure to the material and still there is very small change in volume. So, such materials are actually incompressible material, right, whom you cannot compress, whom you cannot change the volume of such material. So, this nu tending to 1 half, so that is the incompressible limit. Okay. So, we call this incompressible limit. So, usually nu is always less than equal to half, and you see from this formula that G is equal to E over 2 times 1 plus nu. See, what do you expect G to be? Check this experiment of shearing of this rectangular bar. So, when you apply shear stress, the gamma 1 2 should also be positive. If you apply positive shear stress, the angle gamma 1 2 should also be positive, is not it? So, the slope should be positive. So, G is expected to be positive, right. G will not be negative. Likewise, the Young's modulus, look at this graph. When you are applying normal stress sigma 1 1, you expect that epsilon 1 1 will be positive, right, it will not be negative. So, the slope will be positive. So, this means Young's modulus and shear modulus, they are positive. Okay. So, Young's modulus E is greater than 0 and G is also greater than 0. But if G is greater than 0 and E is greater than 0, what happens to this formula here? See, the numerator E is positive and G is also positive, that means denominator should also be positive, right. So, this means denominator one plus nu should be greater than 0. So, that means nu has to be greater than minus 1. So, nu, the Poisson's ratio cannot be less than minus 1, and from here you see that nu has to be less than 1 half, because as nu goes to 1 half you reach the incompressible limit, you cannot go beyond it. Okay. If nu is more than 1 half, just look at the formula for the bulk modulus k. If nu is more than 1 half, then k will become negative, and that is again not expected from physics. So, this has to be greater than 0, right. So, this tells us the theoretical limit for Poisson's ratio is between minus 1 less than equal to nu less than equal to 1 half, right. So, that is the theoretical limit for Poisson's ratio. in case of isotropic materials. So, this is only for isotropic material. All right. And of course, there are also ways to relate the constants lambda and mu with Young's modulus and the Poisson's ratio nu. So, you can relate these two, because after all we had two different stress strain relationship, but it is for the same isotropic material. So, there has to be some relation, is not it. So, we can also relate these two by doing some calculation, and maybe I will give this to you as an exercise, how to relate these two constants. All right. So, this was all about isotropic materials, but this is not all. In reality, the material is, we have all kinds of material. The wood, for example, this is the simplest example which is not isotropic. We say that wood is actually orthotropic material. Just think of a material which is isotropic, which has same property in all direction. So, these days people engrave fibers in the material. So, it becomes a fiber reinforced material. So, those lines, they are fibers. So, when you put fiber in the material, the Young's modulus of the material in the direction of fiber would be different than what is the Young's modulus of the material in the direction perpendicular to the fiber. Okay. So, you see you get directional dependence on the material property. So, they are no more isotropic. So, if you to an isotropic material you put one family of fibers, a parallel line of fibers, then it becomes what is called transversely isotropic material. Okay. So, it becomes transversely isotropic materials. So, they have one Young's modulus in the direction of fiber, but in any direction perpendicular to the fiber it is the same. So, that is why it is called transversely isotropic. In the direction transverse to the fiber it is isotropic. In all directions transverse to the fiber you have the same property, but along the fiber it is different. So, therefore, it is transversely isotropic material, and it has 5 independent material constants. Okay. You can look on Wikipedia to know more about transversely isotropic material. Similarly, to an isotropic material, if you put two family of fibers, let us say you have this material and you put one family of fiber like this into the body and another family of fiber perpendicular to it, but a different fiber. Okay. So, black and blue fibers are not the same. So, in that case the Young's modulus along the black fiber and along the blue fiber will be different, and in the direction perpendicular to these two will also be different. So, you have different Young's modulus in the 3 directions, right. So, they are called orthotropic materials, and wood is one such kind of material. Okay. So, this is orthotropic materials. And one interesting example is wood, and they have 9 independent material constants. So, they have 9 constants. You see the isotropic materials have 2 constants, transversely isotropic have 5, and the orthotropics have 9. and more general anisotropic material, it will have 21 constants. Okay. So, this was all about isotropic stress strain relationship and little more beyond, but this was all for elastic materials, where the stress only depends on strain. There are materials for which stress not only depends on strain, but also on strain rate. There are something called elastoplastic material, where you also have the concept of plastic strain. So, there are all kinds of materials. Okay. So, but for this course we will mostly be bothered about isotropic elastic materials. Okay. So, I hope you got some picture about isotropic bodies. So, see you in the next class. Thank you.